Hi everyone, in this video I'm continuing to take a look at question 13 part C of the 2020 North Sydney Boys Extension 2 trial exam. So in this video I'm going to be looking at part 3 of this 4-part question. So if you haven't already seen my videos on parts 1 and 2, definitely take a look. In particular, have a look at the videos for part 2 because the techniques we use there are very similar to what we're going to need here. So here in part 3 we're told to find the sum of the area of the shaded region in the diagram below, and we have a diagram very similar to the one in part 2, with the key difference being that our rectangles now go outside of the curve, so they sit above the curve rather than below the curve. But apart from that, the approach we're going to use is virtually the same. So yeah, let's take a look. So I've drawn up our diagram as usual, and just like we did with part 2, I'm going to start by working through an example. So we're going to have to think about this in terms of odd and even cases. I think it makes sense to do that. So in terms of our even case, the example we'll use, just like we did for part 2, will be n is equal to 4. I think that's a sensible number. It's not too big, but it's big enough that you can kind of see a few rectangles. So just like it was with part 2, if we've got this range from 0 to 2 and we want to divide it into 4 bits, we're going to have it at half, 1, 1.5, and then 2, and then that creates our 4 bits. So we'll have 1, 2, 3, and then those 3 lines create our 1, 2, 3, 4 equal parts. So in this case, each of these equal parts will have a width of 2 on 4. And the key difference between here and what we had before in part 2 is part 2, if I just flick back, wow, all the way back here. Part 2, we had the same lines to break up the range, but we wanted our rectangles to stay below the curve. So these first and last rectangles had no height. And this midpoint didn't connect to any rectangle. But now it's actually quite different, because if we're thinking about the rectangles that sit above the curve, well, this line here, if I get my ruler, will connect over here to create a rectangle. And this line here will extend outside and then down to create another rectangle. And then this line of point 1, instead of connecting to no rectangles, this time it actually connects to 2. It creates 2 rectangles, the 2 that sit above, like this. So now instead of just having 2 rectangles, we have 4. And now we can think about what the area of each of these rectangles will be. So just like before, it's a fairly simple pattern. So the area in each case will be the base times the height. The base is always going to be 2 on 4. In this case, this first point will be the function at the point 2 on 4. And then this rectangle here will be, again, it'll have a width of 2 on 4, and the height will be the function at 4 on 4. Now, interestingly, this next rectangle will also have a width of 2 on 4, and its height is also the function at 4 on 4. And then finally, we have our last rectangle with a width of 2 on 4, and a height of the function at 2, 4, 6 on 4. So the function at 6 on 4. So that's what we're dealing with. Now, interestingly, we've kind of got a duplicate here. So if we wanted to count up, if we're thinking in terms of the next step where we want to generalize, if we wanted to go 2, 4, 6, we'd kind of need to take this duplicate and throw it out at the end. And now, instead of subtracting something to make an adjustment, we're actually adding something at the end for our adjustment. So we don't have to when we've got this exact number, but maybe I'll do it just to illustrate what we're eventually going to do in our general case. So we'll have 2 on 4 factored out, and that'll be times f of 2 on 4 plus f of 4 on 4 plus, and I'll skip here to f of 6 on 4. And then outside we'll then add our 2 on 4 times f of 4 on 4 again. Now, in terms of now throwing all of these into our function, it's going to be 2 on 4 times, so this will be the square root of, and again I'll just leave everything unsimplified, so we'll go 2 on 4 times 2 minus 2 on 4 plus f of 1 we learned in prior parts is just 1, the square root of 1 times 1, or the square root of 1, so that's just going to be 1. And then f of 6 on 4, we know due to symmetry it should be the same, but I'll write it out anyway. 6 on 4 times 2 minus 6 on 4. And then plus 2 on 4, again, f of 4 on 4 is just going to be 1. So this is going to be 2 on 4 times, let's simplify these square roots. So we'll get 2 on 4 times 2 minus 2 on 4. So that's going to be the square root of 3 on 4, or that'll end up as the square root of 3 on 2, since the square root of 4 is 2. And then plus 1, and then this should also be root 3 on 2. Let's plug it in to double check. 6 on 4 times 2 minus 6 on 4. Yep, that'll get us root 3 on 2 as well. And then plus 2 on 4. Kind of like I did in the last test, I'll just plug this in and get a number, and we can just write enough decimal places so we're confident you get exact. So we're going to get the square root of 3 divided by 2, and we'll have another one of those, so times 2, plus 1 times 2 on 4, and then plus 2 on 4. So that gets us 1.866025404 and so on. And that is going to become our check when we try and generalize this, which I'll do in a follow-up video. So just like I have in part 2, I'll follow up in a separate video so that you have an opportunity to pause and between the end of this video and the next video, think about how you would generalize from what we've seen here. The way I've written it out gives a little bit of a hint, but it's definitely worth you having a think about this and then see how it goes when I get to the next video.